Okay, I've had a request to go over something from the homework, so we're going to start with that. You'll notice we're skipping 5.1b. That's because I'm assuming most of my Block 8 class will probably not be there. So I'm making this lesson something that's more manageable than 5.1b. I think 5.1b is better if you're live for it. This one, it's weak acids, it's race and KB, so it's just like race and Ka, so if they miss it and they catch up with the video, it's not such a big deal, okay? Plus, the quiz, when it comes around, is going to be on 5.1 and 5.2, so it doesn't really make a difference if we sort of mishmash them together. But we had a question from 5.1a. What was it? Which number? Number 5J. Okay. So we have an indicator that is yellow in NaOH. And it is blue in HCl. So what does that tell us about the color of HIND versus IND minus? Which one is yellow and which one is blue? HIND is blue because we threw hydrogens on it and it turned blue. And IND minus is yellow. All right, so that takes us there, and it changes color 3.6 to 5.2. So below 3.6, it's going to be what color? Blue. And above 5.2, it is going to be yellow. And in between 3.6 and 5.2, it will be green. Now, just in case you're wondering, I'm never going to give you a value where I give you exactly 3.6 and you're like, oh, is it green? Is it blue? I just don't know. I will always give you something either 3.7 or 3.5, so you're not wondering, okay? All right, and now we're on J at pH 4.3. So 4.3 is in the transition area.
Will the thing go that way, or
if it's in between 3.6 and 5.2, it will be green. Okay. Where did it go? J, it will be green. And halfway through this transition zone, so we would take 3.6 plus 5.2, and we would divide by 2, and we get 4.4. Okay. 4.4. So if we are above 4.4, then we are primarily IND minus. If we are below, we are primarily HIND. And so 4.3 is below. So even though it wouldn't be by a lot, HIND would be greater than IND minus because we're below 4.4. Does that make sense? Yeah. HIND would be greater than IND minus, but not by a lot. Any other questions? Yes?
Only at the transition point is HIND and IND equal, but if it's even if it's a little bit lower
Yeah.
above, and even if it's just the green part,
Yeah.
it's still
Yeah, they'll still be either greater or less than. But like I said, only a little.
okay.
Yeah. Good. Any other questions from the homework? All right then. So like I said, we are going to take a look at weak bases and KB today because it is, like I said, very manageable because we know a lot of it already from Unit 3. All right. Let's do a review before we get to our weak bases. Let's do a quick review of strong bases. Strong bases are most often what? MHs. Sorry? Metal hydroxides, yes. These fit the Arrhenius definition of a base because what do? They release OH minus in solution. Tell your partner an example of an Arrhenius strong base. I heard NaOH, I heard KOH, I heard LiOH. Okay, those are all really good examples. How many strong Bronsted-Lowry bases are there? Feel free to look on your chart if you don't remember. There are 2. What are they? Tell your partner, what are they? They are O, not OH, O2 minus, and NH2 minus. Okay, so if you've forgotten where to find them on your data booklet, they are these 2 down here. Okay, not the OH and the NH3, but the O2 minus and the NH2, because these are the acid forms. And they're too weak to be acids. Okay? All right. There are hardly any, so in this particular section, we're not going to bother talking about them much. We've already spent some time on them in Unit 3, so we will, or in Unit 4, so we'll come back to those in a little bit, but not right now. Weak bases. All weak bases are Bronsted-Lowry bases. Okay, there are no weak Arrhenius bases. And if they are Bronsted-Lowry bases, what does that mean they are? They are what? They are proton acceptors, yes. So for example, ammonia is a weak Bronsted-Lowry base. And so it accepts a proton from water. And we end up with NH4 plus, and water becomes OH minus. And that's why it's a base, because it produced OH minus. When we were working with weak acids, we could cheat, right? And we didn't always write our full reaction with the water. We would often just be like, HA, H plus, A minus, which is not actually reality. But it was okay to do that, yes, because it all worked. The reality would have been HA plus what? H2O. In equilibrium with H3O plus A minus. And we got away with just doing this if we wanted to, okay? But we cannot do that with bases because because all weak, when working with weak acids, we could leave it out because all weak acids fit not only the Bronsted-Lowry proton donor definition, but also the Arrhenius definition of an acid where they release H plus in water. Weak bases, though, do not meet the Arrhenius definition. Can you make NH3 release OH? Is there any way to make this happen? Just release it. No. So we need to have that equilibrium involving water. So equilibria involving weak bases must involve water or another Bronsted-Lowry acid. As a reactant. So you're always going to have the weak base and something else. Probably if you're just dealing with that weak base, it'll be water. Okay? And weak bases form an equilibrium so they can have a KEQ. And what are we going to call that KEQ for a base? KB. And if we have our weak base equilibrium, we can write the KB expression. Could you please write the KB for NH3? Using this. Just the expression. Not a value, just the expression. Is good? Straightforward enough. We leave out water because water is a liquid. Okay, nothing more to it than that. Whenever you have a KB, though, it should always contain OH, just like a Ka always contained H. On the top. Yes. Oh, it should be concentration of NH3. Thank you. Yeah, I forgot my square brackets. Oops.
Why it's not H2O? We don't include H2O.
Yeah, no liquids.
Why?
Why?
No, not why. Like that example. Like, why do we have like then NH3 twice?
We don't.
I mean, like we have an expression that like in KB.
Yes. Oh, this is, I'm just saying it's the KB of NH3. Yeah? Yeah. Okay. Any other questions? We're good? Okay. Oh,
It's like there's so many K's.
yeah.
How do you know which one to use?
When it's an acid, use Ka. When it's a base, use Kb. When it's a low solubility thing, use the solubility product constant. That's it. Yeah? But I will say, even though that sounds like it might be like a trivial question, it's not, because I will have questions where it says there is a weak base, blah, blah, blah. Please find the pH. And people will then write a Ka expression. And I'm like, nope, it's a weak base. If it says base in the question, write the KB. So like I said, even though that question sounded a little trivial, it's really not, because people make that mistake all the time. They try and use a Ka for a base and it doesn't work. So yeah, good question. All right. So finding patterns, this is some organic chemistry. You are not responsible for knowing anything about organic chemistry, but it will help you see when you're given like an unknown base, how it's going to react as a base. Okay? So our weak bases, one key thing about science is it's all about finding and studying patterns. So what you guys are going to do is you are going to try finding some patterns in all of these bases. These are organic bases. Except for one. No, except, they're not all organic bases, but they're all bases. Let's get rid of the word organic. Okay, there we go. Better. What do all the names of the weak bases, other than ammonia, have in common? You can tell your partner. They end in? Yes. What do a large number of the names of the weak bases have in common? Not all of them, but a large number of them. The names. So we're still focusing on the names. They all end in INE, but a lot of them end in no, the name. What does the name? What do the names have in common? Most of the names. No. Hmm? Sorry?
They are very
LAM, yeah. I'm going to not put in the L, but yeah, they all end in amine, okay? And there's method in my madness why I left out the L, okay? The reason I left off the L is because this part of the name refers to the fact that you've got ethanol and then you've got amine. We have 3 methyl groups on an amine. We have a hydroxyl group on an amine, okay? So an amine is a type of organic functional group. An amine is an organic functional group. Don't worry, we'll talk about what a functional group is in a moment. Again, you are not responsible for knowing what a functional group is, but it will help inform you about why these things are all bases. But before we get to that, what do all the formulas of the weak bases have in common? They have H. What else do they have?
Oh, yeah, H carbon.
Do they all have carbon? No. They all have nitrogen and hydrogen. And do you know what an amine is?
Functional.
It is a group that contains N and H. Okay? So this functional group is called an amine. And you may have heard of this in amino acids. Amino acids contain amine groups, and they also contain a carboxylic acid group. So if you've been taking biology, that might sound familiar to you. Okay. Again, do you need to know these categories of amines? No, you don't, but I'm just going to introduce it to you so you've seen it. Nitrogen, if you remember nitrogen, how many valence electrons does nitrogen have? It's in group 15. How many valence electrons?
to 16. No, it's 4. 2, 4, 4, 16. Right?
Okay, how many valence electrons does lithium have? Group 1. 1. How many does beryllium have?
2,
2. How about boron?
like 5, 3.
3. How about carbon?
4,
That's why carbon can form 4 bonds, because how many does it want?
4,
How many do they want to be stable?
4. No.
Okay, let's carry on. Nitrogen has,
5.
oxygen has. Okay, 1, 2, 3, 4. Nitrogen has 5. How many does oxygen have? 6. Okay. Chlorine has 7. Neon has 8. What group is neon in?
What group?
What do we call them? Noble gases. What do we know about noble gases?
They're not red.
They're not reactive. Why are they not reactive?
They can't.
Because they what? Because
Can't.
they can't? Okay, but why can they not?
Because
They have a full valence shell. So carbon has 4 electrons. How many would it like to have? If it has 3 more, that would give it 7.
Oh, wait.
Is 7 stable?
No.
No. How many would carbon like to have? 4 more to give it a total of 8. So let's say we had carbon. One, 2, 3, 4. We could make that stable by having it bond with hydrogen, 4 of them. Yeah? Which would give us H, 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 H. And we can replace that with lines representing the bond rather than the 2 dots representing the bond. Okay, don't worry about why it's a double bond. We're just going to stick with single bonds, okay? Because we don't have time today to go into that, and it's not really relevant to what we're doing. Okay, but do you see how having 4 unpaired electrons, carbon can form 4 bonds? Okay, remind me, we're in group 15. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. How many unpaired electrons? 3. Okay, so we had 5 valence electrons, 3 unpaired electrons. So how many bonds will nitrogen usually form, unless something's a little weird? It will usually form 3 bonds. Just like with the carbon, we could attach hydrogens on each of those, and hydrogen would allow an electron to go in there. So when we look at nitrogen, you'll notice that each of these amine structures has 1, 2, 3 bonds. And do you remember what we call these electrons that are not involved in bonding? That's called a lone pair. Okay? 3 bonds, lone pair. 3 bonds, lone pair, 3 bonds, lone pair. Yes? Now, on the ends of each of those bonds, you might have a hydrogen. If you have a hydrogen on the end of each of those bonds, then we have NH3. And we know that NH3 is called ammonia. Yeah? Now, if we take one of those hydrogens away and we replace it with an R group, and what the heck is that R doing there? R stands for the rest of the carbon chain. Okay, there's going to be a carbon there. Maybe it's 1 carbon, maybe it's 2 carbons, maybe it's 6 carbons, maybe it's a ring structure of carbons, but anyway, there's going to be a carbon there. Technically, that's not what R stands for, but that's how I've always thought about it, and it's always made so much sense to me, so I'm passing that along to you in the hopes that it will also make sense to you. So this group here could be we could have a bond and then a CHHH, right? We could have our N, CHHH, or we could have an N and we could have a C, HH, C, HHH, or we could have any structure that involves a carbon there, okay? If we have that, that is called a primary amine, okay? If we have 2 carbon chains, so the R is a carbon chain, R is a carbon chain, and when I say chain, it doesn't really have to be a chain. You could have just a single carbon, but it's at least 1 carbon. That's called a secondary amine. Okay, and if you have the N attached to all of those things, that's called a tertiary amine. So we have a primary amine with just 1 of those carbon chains, a secondary amine, and we have a tertiary amine. Tertiary means 3, okay? Primary, secondary, tertiary. Have you heard those words in terms of like folding of proteins? Primary structure, secondary structure, tertiary structure? Yeah, okay, so it's the same sort of language that we're getting there, primary, secondary, tertiary. And if you're unfamiliar with it, you can use the abbreviation primary, secondary, and tertiary. But do you need to know any of that for Chem 12? No, you do not. I'm just leaving it out there because it will come in handy in university if you are studying chemistry or biology, both of them, okay? At any rate, an amine functional group, they are found in many carbon-based, many organic or carbon-based compounds, including amino acids. The acid part of an amino acid is another functional group called a carboxylic acid group, which gives us all of the carboxylic acids. Those are the ones that have that COOH group. Do you remember how we looked at COOH and said that's an acid? Well, that's what we get when we have an organic acid. Why are they called functional groups? Because they tend to all function in the same way. When you have COOH, it behaves as an acid. When you have an amine, it acts as a base. Yes? So the functional group means that when you have that pattern, when you have that little group in a molecule, you're going to have at least an area of that molecule that acts like a base. If you have a carboxylic acid group, it's going to act as an acid. So none of this is in the grade 12 curriculum. It will not be tested, none of that. But what we can do then is we can say we know that when we have amines, which is like the NH, or even just N, and we put it with water, these are proton acceptors. Why are they proton acceptors? Well, if you were a little hydrogen floating around and you had a positive charge, you would look at that little lone pair over there and you would say, ooh, look at that lone pair. That's pretty negative, and I am positive. Therefore, there is an attraction. So what will happen is you will end up with N with the original 3 H's. And then you'll have that plus charge there still, okay? So it is that lone pair on the nitrogen that allows it to grab onto the hydrogen. So amines reacting with water. Basically, all you're going to do is you're going to take a hydrogen and you are going to put it onto the nitrogen. So instead of having NH3, you'll have NH4. We'll take a hydrogen and we'll put it onto the nitrogen. So instead of having N2H4, we will have N2H5. And it's going to have a positive charge because we've added an H plus. Now, in this next one, where do you think the hydrogens should attach to? The hydrogen will attach. Will it attach in here? Will we end up with more hydrogens in there, or will the hydrogen go on the nitrogen? It'll go on the nitrogen. Okay, so here comes our hydrogen. It goes on to the nitrogen, and so when we write the formula, we throw it onto that nitrogen. Over here, once again, when our hydrogen comes over here, do we add the hydrogen there or do we add the hydrogen there? We add it to the N. So it doesn't go to the C, it doesn't go to the carbon hydrogens, it goes to that nitrogen and adds on there, so we end up with H3. Okay, and similarly, this hydrogen is going to go onto the nitrogen, and there we end up with our H3 plus. Where do you put the hydrogen accepted from the water? Onto the nitrogen. So try writing the equations for the reactions of the following amines with water. This part is something you need to know for Chem 12 because I might give you like random base, right? Some weird amine that you've never seen before, and you will need to react it with water to write its weak base equilibrium and then do its Kb expression. So give it a try. You can, yes. Sorry?
Let's say if it's the last one, like CH3, is it R group?
CH3 is not an R group. The CH3 is an R group. I'm so sorry. I was thinking functional group. Yes, it is an R group. Yeah. Yeah, exactly. So this would be a secondary amine because it's got 2 carbon groups on it. This one would be a, well, I don't even know what that would be. I guess it's only got 1 hydrogen. No, it's just got, I don't know. I don't know what that one's. Yeah, yeah, exactly. Okay. All right. So look, here's our little old lady again. And what is the little old lady? The little old lady is weak. Yes, she is weak. That is the whole point. And she is carrying what? She's carrying a bag of rice. So anytime it's weak, you are going to use rice. Okay? Now, if remember when it was an acid, the bag of rice fell on the ground, but now it's a base, so she makes it to her home base. Yes? So there's no rice falling on the ground, right? So the rice does not fall on the ground, or at least she picks up her rice, makes it to her home base. So there's no rice on the ground. For the crows to eat. But she still has her bag of rice. So you're going to use rice. Okay? But the crows are happy because they found some kebab on the ground. And they cry, kebab, kebab. So it's KB. 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 So you're going to use rice and KB when she makes it to her home base because they're now eating kebab. Okay, so for a weak base, you're going to use rice and KB. Probably you didn't need all of that, but like I found a picture of kebab and then I got the crows eating. I don't know. I was just very happy with the picture. So sometimes you're just indulging me in my silliness, okay? Yeah, and I even wrote that here. I'm a little too obsessed with this story, but there we go. Okay. One of the biggest mistakes students make, and this is what I was saying before, is that when working, when working with weak bases, they will try to use Ka. Sad face. Okay? If you use a Ka when you're working with a weak base, that's going to be wrong. I don't want you to make that mistake. So every time you are asked for the pH, every time, or if you're asked for hydrogen or hydroxide or POH or the color of an indicator, you have to ask yourself, and we're going to put like 3 stars here. This is important. Important. Do it every time you're asked for pH, POH, hydrogen, hydroxide, color of an indicator. Is the solution an acid or a base? And is that acid or base strong or weak? If it's weak, you use rice. If it's an acid, you use Ka. If it's a base, you use Kb. And if it's strong, what do you use? If it's strong, you do not use rice and Kb or Ka. You just use stoichiometry. Strong stoichiometry. Okay? If it's weak, use rice, and whichever K is appropriate. Just because a question asks for H+, do not assume you are working with an acid, because you can be working with a base, you can find the hydroxide and then find the hydrogen. So you might have a question where it says calculate the H+ concentration of a 0.1 molar solution of the weak base aniline. So that means that aniline is going to act as the Bronsted-Lowry base. It will accept a hydrogen from water, which acts as the Bronsted-Lowry acid. Please predict the products. And because it is weak, we're going to use rice. And because it is a base, we're going to use KB. And also we're going to use KB because guess what? It gave us a KB. Why would it give us a KB if we didn't want to use KB? It's possible, but it seems silly. Okay, go ahead and do this question. You know all the tools you need to do. See if you can do it. It's no different than Ka, just this time it's a base.
Oh, this one we put just put X.
You need to figure out what you put where. You've got that green information, yes? Mm-hmm. No, our initial concentration, you got a 0.1 molar solution of the weak base. That's the initial. Right? Yeah, yeah.
Okay, you can see where that is. And that's as it is, as we want to participate, it becomes something, so now this is, this. This, that's, right. Not only for this, that's, this contribution. So it's considered to be. No, I didn't.
Yes, for the ice.
No, minus.
Yes, yeah, no, this one is widening, but because we're not good liquid, right? Thought about that. I might lose marks if I do that. No, don't split.
That's a liquid. What's happening?
I know, you assume X and get true, no.
Not saying anything, but not. Water doesn't help. Yeah. And I'm a little concerned as to why, but. Or. Reactants on the top. Yeah. Yes, yes.
Did you get concentration of OH 6.56 times 10 to the minus 6? Yay! But our question asked us for the concentration of hydrogen. How do we go from hydrogen hydroxide to hydrogen? What do we use?
Convert it to KW.
Kw is equal to the concentration of hydrogen times the concentration of hydroxide. And then we solve for hydrogen. Hydrogen is Kw over hydroxide. So that's going to be 1.0 times 10 to the negative how much? Kw is 1.0 times 10 to the negative 14. And we're going to divide by our hydroxide, 6.56 times 10 to the negative 6. And we get 1.52 times 10 to the negative 9, but we only want to have how many sig figs? 2 sig figs, so that's going to round to 1.5 times 10 to the minus 9 molar, and that is our hydrogen ion concentration. Is good? All right. So very, very similar to what we did 2 units ago, yeah? And now we can try the next one. But I'll give you a minute to finish this one if you need to.
You know what? Yeah, lots.
Okay, now the next example, are you ready for the next example? Yeah? Okay. The next example is very, very similar, except that this time, instead of finding the pH or the H, this time we are going to be finding the Kb. Everything can just go in there. Yeah, perfect. Good. The other thing that I've done here, just to make it a little bit different, is I've given you this great big long formula, right? C17H19NO3. What if you don't want to write that down every single time? Yeah? You could say, let's, because it's a base, let us let B represent the formula for morphine. So instead of writing out all of this, which is so long and awkward, we're just going to write B instead. But if you do this, you must write this statement, okay? If you want to replace it. If you want to simplify the formula, you must write this. If you don't want to, feel free, write out the whole dang thing. Yes? And if you were like, oh my gosh, this thing, I don't know, where would the hydrogen go? You could just stick it anywhere. You could say HC17, H19, NO3. You could say C17, H20, NO3. You could say C17, H20, NHO3. You know what I mean? Like, it doesn't really matter where you stick it because you don't have enough information to figure it out. Yes? Or you could stick it on the end. C17, H19. Oh, whoops, that should be 19. NO3H. Honestly, I don't know where it goes because I don't know what that actual structure looks like. Yes? So in that case, I figure it's just going to be way easier to have B because when I write my weak base equilibrium. Then I'm just going to say B plus H2O. And I think at this point, it would be very good for you to remind yourselves that that one is aqueous, that one is liquid, so that you don't try and include it in your equilibrium expression, your KEQ expression. And then, does it matter if you put HB or BH? Not really. Either of those would be fine. Okay, so choose whichever one you want there. I'm going to go with HB plus. And then, do you guys think you could solve the rest of this? Go for it.
Yeah, that's just.
Where does it come from? I don't know about that.
Excellent. Do you have the block?
Wait, now, yeah, so did you use the pH at all for this? Yes, you're supposed to, but from pH, you can find pH, and then find the concentration of OH. Do you remember? pH plus pOH. Yeah, I know, no, but then,
Any other content?
no, but the thing is, but can you just use rice?
Yeah.
Well, what is the initial concentration?
Or B. Well, you're still supposed to find OH like the concentration, and you can do that. You will not solve the problem without knowing.
Can you just do? Oh, shoot, oh yeah, we have to find the
Yes,
concentration.
Yeah.
Are you able to answer both 4-mark questions
What question?
for the test? The 4-mark ones.
What's the 4-mark one?
They wanted the last two.
The last two, yeah, sure, both of them. I feel like the 4-mark one easier than the 2-mark one.
Yeah.
What?
The one where like. Right.
Yeah.
That was. They're basically just the same question. Except you gotta do a bit longer for both of them. Yeah, definitely.
Yeah.
Wait, PKW is pH minus POH. That makes sense.
Okay, so PKW is equal to the pH plus POH. Yes? All right. And so if you want to then find the POH, that's going to be PKW minus pH, which is 14.00 minus our pH is 10.5. Once you know your POH, you can find your concentration of OH minus. Do you remember how to do that? 10 to the negative POH, yes. A couple things to remember whenever you are given the concentration of the solution, is that the initial concentration or the final concentration? That's always the initial concentration. If we give a pH, is that the initial pH or the final pH? Initial or equilibrium? What's our initial concentration of hydroxide? 0. Right? Because the moment we put this into the water, this is 0.15 molar. These are 0 and this is 0. So right when you put it in, the pH is still 7. Yeah? Because it hasn't ionized yet. Then it ionizes and these concentrations go up and this one goes down. And before you start putting in X's, you should think to yourself, do I have unknowns? Is this change known or unknown? Well, I've just solved for my concentration of hydroxide. So that means my concentration of hydroxide can go right here. And I'm not going to write the whole thing. I'm going to keep that number in my calculator. Okay, so I have 3.2 times 10 to the minus 4, which means my change is 3.2 times 10 to the minus 4. I started at 0 and I went up by 3.2 times 10 to the minus 4. 3.2 times 10 to the minus 4. 3.2 times 10 to the minus 4. And this one went down by 3.2 times 10 to the minus 4. Now, when I subtract that from it was 0.15, wasn't it? Yeah, 0.15. I get 0.1497.
So can we just round it off? Again?
I don't know. I'm going to leave it like that because I'm like, why don't I just let it be the real number? Yes? Why not just let it be the real number? Because it does appear to change it maybe a little bit. Yes, maybe not. Maybe it's not enough to worry about, but maybe it is. So now what I'm going to do is I'm going to say, okay, I've got that. I want to find KB. So write your KB expression. KB is equal to concentration. I'm going to use HB plus. You could use BH plus, doesn't matter. Times OH minus over concentration of B equals 3.2 times 10 to the negative 4 squared divided by 0.1497. And I'm actually not using 0.1497. I'm using 0.149683772. And I'm 1 over xing it. And now I'm multiplying it by my memory recall, which is 3.16227766 times 10 to the minus 4 squared. No, that's not right. Equals. I think something went wrong. Do you get 6.7 times 10 to the minus 7? I think that's wrong. Is it right? Okay, cool. I was a little scared because when I squared 3.2 times 10 to the minus 4, I got like 0.1 or something, like a real like rounded off number. But anyway, that's what we get. How many sig figs should we have? This one's nasty. We have to go back and we say, what numbers were we working with?
3 sig figs.
We were working with this.
Oh.
Okay. And here we've got 2 sig figs. Here we only have 1 sig fig. So this has only 1 sig fig. So this should have only 1 sig fig. So this is going to round to then 7 times 10 to the negative 7. Yeah? I need a copy of this book.
So what's next? Okay.
We have 10 minutes left. Should we do example 3? Yeah? Okay, let's do example 3. Because we only have 10 minutes, do you want me to do it with you quick? Yeah, rather than, figure it out. Some of you have already figured it out on your own, and you probably could do it. But let's just do it quick because we only have 10 minutes. We have a weak base. Therefore, if we have a weak base, what tools will we be using? We will be using Rice and what else? Rice and KB, not KA, KB. All right, so we know that we have a weak base. We don't know what it is. So let's just call the weak base, let B represent the weak base. And let's write the weak base equilibrium. We got B, which is aqueous, water, which is liquid, in equilibrium with HB plus aqueous plus OH minus aqueous. And we are going to be using a Rice table, so let's write in our R, I, C, E. Water doesn't have anything in there. Do we know the initial concentration of the base? No, we do not. It says, what is the concentration of the base? Whenever it says the concentration of the base, that's always the initial. When it's given to you, it's the initial. When it's asked for, it is the initial. Doesn't matter if we give it or ask it. So that's what we don't know. So let's let that be X. That's what we don't know. Can we fill in the initial concentrations of HB and OH? Can we fill in these ones? Those are always 0. So let's just put those in. We can always also fill in. Yeah. We can also always fill in that this is going to go down, this is going to go up, this is going to go up. Now you have to decide, are those values, are those changes known or are they unknown? They are known because we have a pH. All right. This time I'm going to go the other route to get to hydroxide. So I'm going to say, okay, I could take my pH of 10.16, and I could say that my concentration of hydrogen, this is just, you could do it the same way as we did the last one where you take pKw and subtract, but this one, I'm going to say that's 10 to the negative pH, which is 10 to the negative 10.16, which is 6.92 times 10 to the negative 11. Hydroxide then is equal to, if you remember, Kw is hydrogen times hydroxide. So OH is going to be Kw divided by hydrogen, which is 1 times 1.0 times 10 to the negative 14 divided by 6.92 times 10 to the negative 11. And we get 1.445 times 10 to the negative 4. That is our hydroxide ion concentration. And that's going to go right up here. So that's going to be 1.4 times 10 to the negative 4. Again, I'm not going to write all my digits because it's a pain in the butt, but I've got all my digits in here. It's actually 1.445439771 times 10 to the negative 4. Okay. And because everything's 1 to 1 to 1, this is also going to be 1.4 times 10 to the negative 4. This is going to be x minus 1.4 times 10 to the negative 4. Whew. Okay. This is a base, so we will be using Kb. Hopefully we are given a KB value. Let's go check. Yes, 8.40 times 10 to the minus 7. And we've got both of HB plus and OH minus are 1.4 times 10 to the minus 4, and that's squared. And that's over X minus 1.4 times 10 to the minus 4. Easiest way to do the algebra on this one is to swap this and this. Okay, so let's bring our X minus 1.4 times 10 to the minus 4 up to the left-hand side. We'll keep this here, 1.4 times 10 to the minus 4 squared, and we'll bring our 8.40 times 10 to the minus 7 down here. Okay. So 1.4 times 10 to the minus 4, I'm going to square that. And I'm going to divide it by 8.4 times 10 to the minus 7. And I get 0.02.
Wait, why don't we do X is insignificant for this one?
Because X is what we're looking for. And it's a big number, right? It's the concentration. It's the starting concentration. It's not small compared to the starting concentration. It is the starting concentration. 0.2487. And I got X minus 1.4 times 10 to the minus 4. So X is equal to 0.02487 minus 1.4 times 10 to the minus 4, which is minus, memory recall, equals 0.02473.
That number was even insignificant.
Huh?
That number was before it wasn't insignificant.
Yeah. Okay, now we have to go back and say sig figs. We got 2 sig figs here. Well, you know what? Honestly, don't worry about the sig figs. We'll look at those next day. Homework is questions 1 and 2 from each section. 1 and 2 from A, 6 and 7 from B, and 10 and 11 from C. Okay? 1, 2, 6, 7, 10, 11 on page 29.
Okay, yeah.
I'm gonna be away for like.
I'm glad.
Awesome. Okay.
Letting you know. I'm going
Okay.
right now.
That's amazing. Yeah. Okay, you got your book. I assume that you will not have tons of time to be working on it. Yeah,
I just want.
yeah.
I'll
Okay.
come back to it, yeah.
Okay, okay.
Thank you.
Yeah,
Hello.
Hi.
Lab. I forgot it at home.
bring it in on Monday. No problem.
Thank you.
Yeah. Have a good weekend.
Oh yeah, so weekend. Yeah.
Right? I'm so excited.